Let's get straight to it. Let's see if you understand what's meant by an arc versus a chord. So looking at this diagram, if I were to write out in symbols RS and I put a straight line segment over that, versus if I were to say RS with this curve over it, you should know that this one's the chord, and that's our red straight segment, and this is our arc, in this case our minor arc from R to S. And so this chord RS is cutting off actually two arcs. I've named the minor arc RS here, and then there's our major arc going all the way around through T first right here. So remember how we name those? Minor arc is with two letters, RS, straightforward. Major arc tells me I have to start at R but pass through T, then stop at S, going the long way around that. But something to remember, when we say the arc of chord RS, we are always talking about the minor arc. So we're going to be associating some arcs and some chords together today in this video, and you need to just remember, because I probably forget to mention it, it's become kind of ingrained in me, it's always the minor arc. So it'd just be RS. Okay, so let's get to it. We have some theorems. Theorem number one, let me just kind of get you set up for this. We're going to talk about chords. So if I have a circle and I just start drawing some chords, I've got some long ones, I've got some short ones. Just depends on which endpoints I pick. There's a little short one you can't even see. There we go. But the longest one is always, of course, the diameter. What happens if I take two congruent chords? So I start with a circle and I have two chords that are exactly the same length. Let's tick mark those. This segment RS is exactly the same as AB. What does that tell me about the arcs of those chords? Well, you might guess, and you'd be right if you say that that means the arcs would also be congruent. So arc RS would be congruent to arc AB, and I put that right on the curves of the circle. Congruent chords is always going to produce congruent arcs if I'm in a circle or if I'm doing it in two congruent circles. So let's summarize that in a statement. So our chords RS and AB are congruent. Therefore, our arcs for those chords, arc RS is congruent to arc AB. Make those curvy. And it's important to realize that that goes backwards as well. If you start with this end part, if you've got congruent arcs, then you can then go back and conclude that you had congruent chords to start with. So this is bidirectional. Let's put double arrows on this. It goes both ways. That's theorem one. Now theorem two also says that if you start within a circle or you do it in congruent circles, you've got two chords that are congruent to each other. So it starts out the same way. What does that tell us about the center? Let's review this again, what we were just talking about with chords. We have different lengths of chords. So if I start far away from the center, I get these short chords. And as I draw chords closer and closer to the center, I get longer and longer chords until I get to the center. And then that's the longest I get. Then they get shorter again as I move away. So if I have two chords that are congruent, AB and ST in this case, what does that tell me about their distance from the center? Well, it tells me they're exactly the same distance to the center. So that's the perpendicular distance right here that you see. This would be exactly the same for both chords. They're equidistant to the center. It works backwards as well. So this tells me if I have congruent chords, they're equidistant to the center. But if I'm looking at a diagram and I see two chords marked equidistant to the center, I can go back and conclude that they were congruent chords, the same length. Let's look at some examples of how these are applied. In our first example, we've got to find x, which is the measure of our minor arc AC, and we don't have much to go on from that except for these two chords that are marked as 7 long. So AB is 7 and AC is also 7. They are matching lengths, congruent chords. Therefore, they mark off congruent arcs. So AB, do I know it? I don't. But I do know it's the same as AC. I can use the exact same x here as I see right here. They are the same. And that gives me all the circle all together. So I see two x's in there, my given and the one I matched, plus a 90. And they make up the whole circle, 360 degrees around. So doing a little bit of algebra, we can figure out the value of x. Let's take away the 90 from both sides. That's going to bring it down to 270. And dividing by 2 on both of those, I believe that's 135 degrees, which would be the solution. 135 degrees. Okay, now in this circle, we got circle R. That tells me that R is the center. And two segments, TS is 21 and UV is 3x. I don't know much about those except I'm noticing from my second theorem that they're both 6 units away from the center. We have them equidistant to the center. So that means that TS would be exactly the same length as UV. Those two chords would be congruent. Let's substitute what they are. TS is given as 21, and we can set that equal to UV, which was given as 3x. So 21 here and 3x here. If you can't read that very well, but we got it in the statement. So just dividing by 3 gives me x is 7. And then one more example from these two theorems. We are going to use these two circles. Let's highlight the given information here because I don't want you to gloss over that. These are congruent circles, exactly the same size. And we are still looking for x here. So I've got TU as a chord with the given. So I've got this arc TU given here as 162 degrees. And I see this arc here and it doesn't match. I hate that. I'm hoping to get a match. And so what I'm going to notice is that's my major arc. What's the minor arc for YZ? What is this? How can we figure that out? Let's just subtract our major arc away from 360 in our circle. And what do we come up with? The exact same 162 degrees. So I see I've got these two congruent arcs and they're two congruent circles. So that's all the information I need. I'm going to highlight those. That's all the information I need to say that these are congruent chords. All right, so I'm going to clear this space out a little bit. That means I can set these two chords equal to each other. These would be the same length. All right, so let's do the algebra. 9x minus 78 set equal to 3x. Okay, if we subtract the 3x over, we've got 6x minus 78. Now we're down to 0 here. So if I add the 78 over, 6x equals 78. Dividing by 6 is 13. X is 13. That's those two theorems. Let's take a look at our third theorem for this lesson. In a circle, a diameter, the diameter here is CD, and that diameter is perpendicular to a chord. So let's actually put that in. Let's mark that we have a right angle. If that diameter is perpendicular to a chord, what does it do to the chord? Can you guess? It bisects the chord, and it also would bisect its arc. So we can tick mark that it's gotten divided equally. That chord would be chopped in half. Its arc that matches would also be cut into 2 equal pieces. Pretty nice. It's all due to the symmetry of the circle. And then what happens if we go backwards? The perpendicular bisector of a chord. So if we have this to start out with, what does that tell us about the chord? Well, we're thinking backwards here. That would tell us that this is a diameter. And maybe it's not a diameter, maybe it's a radius, but either way, it's always going to contain the center of the circle. So if we ever see a chord, I'm going to draw another sketch of that. If we ever see a chord in a circle, and we've drawn in a perpendicular bisector, so we see it's gotten chopped in half at a right angle, then we know that the center is sitting on that chord. And that means it's a diameter. That is actually a very useful theorem. We'll see a lot of examples of how that applies to real stuff. Let's just use it in a math problem though. We're going to find x here again, and I don't see a whole lot of information. And kind of the trick to this is to look at the right angle right here. That right angle tells me, and it comes from the center at a right angle. So all that put together tells me that this chord just got bisected. That same 36 that I see here can be added over here. Now, how does that actually help me find x? Well, it doesn't unless I add something to my picture, and that goes back to the very beginning of our unit when we learned that a radius, this 39 here, can be drawn anywhere and it's going to be the same. And so what I'm going to do is I'm going to draw a radius right here to connect it to the endpoint of this chord. And the reason I'm doing that is because it gives me a nice right triangle that I can use all my right triangle skills, my mad skills, to solve. And I always like to draw that same triangle kind of outside of the circle because it's going to get sort of messy in there. And let's take a look at what we know. We know we have a 36 leg. And we know that we drew a radius in, and the radius of this circle is 39 no matter where I draw it. So that same 39 can go here, which is the hypotenuse of my triangle. And then I can find this segment. Now I'm not going to call this x because x is here. This is a different thing. Let's say this is y. So if I solve for y, then it might help me get x. I think it will. How do I solve for y? Well, you guessed it, it's the Pythagorean theorem. So using 39 as the hypotenuse, y squared plus 36 squared is going to equal 39 squared. And I believe this is a triple, but I'm going to do the workout. Those of you who know your triples, you can do this really quick. Think about what 39 and 36 can all both be divided by, and you'll see it faster. Y squared plus, and 36 squared gives me 1296. 39 squared is what it equals, 1521. Subtracting, we get y squared alone to be 225. And then y would be the square root of 225. Square root of 225 is 15. That's a nice perfect square. And I actually knew that because this is a triple. This is a 5, 12, 13 triple that's been multiplied by 3 to give me 15, 36, 39. For those of you that saw that. Okay, so y is 15. Now, how does that help me get x? We should have probably talked about this before, but remember, any radius is the same. And this is a radius from the center here. So this is 39 right here. And that means x and y together make 39 because they form a radius. So to get x, I just have to add those together. X plus y is 39. And I just figured out y is 15, so x plus 15 is 39. And subtracting gives me my final answer of x is equal to 24. 24 right there. Okay, so here's another example. Lines all over the place. Your job is really to isolate the pieces you need. And right triangles really come into play with this theorem. So let's take a look at the right triangle. We see the right angle, and it comes to the center. And that means that it bisects this chord. That same x can be brought over here. There's our theorem. Continuing the right triangle, what do we know about these sides? This is a diameter. So what's the radius of our circle? 44 cut in half would make it 22. Okay, let's clear that out. So I'm going to add that 22 to my picture. And, oh, I forgot. I always do like to draw that right triangle kind of separated because, again, that circle gets so messy. So we've got the same x. There's the right angle in our 22. We do need to have some information about this other leg, this little short part right here. Again, the key feature of this is the radius. This is another radius right here. Find all the radiuses you can because that's free information. That's another 22. Only this time it's been chopped into pieces. So we need to say that the 22 of the radius, take away that 19, and we would see that we have 3 left over for this little piece right here. And that's going to add to our triangle. Okay, so we're ready to go with our Pythagorean theorem. Let's do it. It's going to have a 22 as a hypotenuse. That's going to put x squared plus 3 squared equal to 22 squared. These I don't think are a triple, at least if it is, I don't know. I don't think it is. But I do know that x squared plus 9 is equal to 22 squared. 22 squared on the calculator is 484. So if we subtract that 9 off, we get that down to 475. And then our final square root, 475. Now if I want to keep this exact, I'm going to divide that down. So I know that 25 goes into that. That's the same thing as 25 times 19. So in square roots, and then perfect square 25 is 5 radical 19. There's our exact answer. Of course, if I wanted a decimal, and it doesn't say here, I would just go back to the square root of 475 in my calculator. Let me punch that in real quick. And that's about 21.8 if I'm rounding to the nearest tenth. Okay. So those are 3 theorems for chords. Get a good summary on those. See if you can say those all in your own words, and also do the try these, of course. See you in class.